Everything in the world has a mirror image, save, of course, a vampire. And that's what we're going to talk about today, mirror images and their relationship to chemistry. Well, we're going to start talking about gloves. Gloves are chiral. That's a word that comes from the ancient Greek meaning hand or handy. And a left-handed glove is not the same as a right-handed glove, right? I can easily put on a left-handed glove, but I can't put my right hand into it because it has a certain property that we call chirality. It has a handedness. They're mirror images, but they are not superimposable mirror images, right? When I put one on top of the other, it's not exactly the same. Now let's get down to molecules. It looks like these are the same, doesn't it? You have a black atom in the middle, and you have a green, red, blue, and white around them, and that's exactly what you have here. They look identical, but they're not. They are mirror images. It is as if there were a mirror here, and this is a reflection of that one. And no matter what I do, I cannot superimpose them. If I match the red and the blue, if I try to match the red and the blue, the white and the green don't match. Similarly, no matter what I do, I cannot make these match exactly. The reason that these molecules exist in these two non-superimposable mirror image forms, we call them enantiomers, is because the molecule has no plane of symmetry. And objects that don't have any symmetry are not superimposable on their mirror. So why should this matter? Because molecules that can exist in such mirror image forms do not necessarily have the same kind of biological activity. When they flow through our bloodstream and try to enter cells, it is very much like trying to put a hand into a glove. There are receptors on the cell, and if the molecule fits exactly, it can enter the cell and do whatever it does. If it doesn't have exactly the right structure, it cannot enter. Where does this come into play? With a large number of molecules. For example, a molecule called ketamine. Now, this is a very complex molecule. And if we would reflect it in a mirror, and if I were able to pick up its mirror image, I could not make it match. It would not be superimposable. Now, it turns out that these two molecules don't have exactly the same activity in the body. You may have heard of ketamine as a painkiller, as an anesthetic, but it is also now being used as an antidepressant. But it turns out that one of the mirror image isomers has greater activity than the other. So originally, this molecule has been off patent for a while. And pharmaceutical companies, of course, want their products to be on patent. You can charge more money for them. So what the company now has done is separated the two types of ketamine, and they are marketing only one, which supposedly is the more active form. And they've been able to get a patent on that. So it's very interesting, both in terms of marketing and also in terms of chemistry. So next time you hear the word chirality, you can think of vampires who do not have a mirror image, as opposed to a molecule which, because of its lack of symmetry, has a non-superimposable mirror image, and that has biological consequences when it comes to designing molecules. An antidepressant, just what one might need if you ever encounter a vampire.